point and from the cloud and the nearest point from the centers that you're making is minimized.
Yeah, great. So given P, say subset of R2, I'll put here, or any metric space actually. With, we'll say P finite. If you want to find a set of centers, subset of R2, such that size of this is K, and we minimize the distance between this C. And here, this will be called switch this backwards. This is really called the Hausdorff distance. And we can define this. We're going to minimize, this is all finite, so I can use mins and maxes over the maximum. Oh wait, this is just maximum, sorry. Oh. No, it is a minimum over maximum. My thinking is not straight this morning yet. Minimize overall C in C. Maximizing overall P in P of the distance between C and sorry, I'm really not thinking right now. Maximum first, maximizing overall points in big P, minimizing overall. Yeah, so for each point in P, we find the closest point in C. We find the closest C and C. Is this a metric? Anyone? Well, let's check the properties one by one. What are the properties of being a metric? Who can share one? Share with us one of them. Oh. Oh wait, we have a chat person. Okay, I was just the triangle inequality. All right. Let's look at this person. I've never set up a poll before, so this is really exciting right now. Let's try it. All right. Oh, that was so cool. All right, I've launched a poll. "14 of 27 people have responded." All right. So we've had that for 45 seconds. I think we can end the poll. Cool. All right. So it's pretty split, but it is not a metric, but we'll figure out why. But it's pretty close to one, and we do use it a lot. So no. But now the question is why, right? Okay, let's first see triangle inequality as suggested by Ben. Okay. We need to think about so let's first think that this is actually a metric that goes from some power set of R2. I'll write it like this because putting 2 to the R2 would look funny. Across the power set of R2. So these are subsets of R2 to R, right? So to think about what our domains are. So power set of R2. Okay, so does the triangle inequality work? So if I had, well, this one's a difficult one to think about. So if I have, well, let's start with a triangle. This is my P, and maybe the circle is my C, right? For each point in P, I'm going to find its closest point on the circle. Maybe then, maybe that goes there. Something like that, maybe. And right, and we'll say that maybe this is where this distance is maximized. So this point realizes the maximum distance. Okay. Now, if I look at some other set, we'll call it Q. This is Q. The distance, and so distance from C to Q. And so we want to look at, why did I make this so hard for myself? It's probably going to be something like this point here. Realized by this one. Okay. And now, we go back to the distance from P to Q, right? Well, what I want to do is I want to minimize the distance between C or P and Q, right? Q and Q, P. Right. Now for this is my Euclidean distance. So we know that this is a metric. Okay. So then let's let CP is the closest point from little p to C. Then distance of PQ is equal to the maximize over the minimize of d of PCP plus d of CPQ. Okay. Oh, so this is not less than. This is strictly less than. Oops. I need to put this in here. Okay, there we go. Less than or equal to P and P, Q and Q. Okay, so what we can do is we can actually split this up here into two pieces, right? We can kind of take the maximum or the minimum over both sets. And if I look at this first piece, right? So if I do max min d of PCP plus max min d of CPQ. Okay, and I'm still taking over P and P, Q and Q, P and P, Q and Q. Okay, but this, right, is equal to the distance between P and C by definition of CP, right? And then this piece here, what I'm doing is for each point in P, I find its closest point in C, and then I take that, find that's closest point. Okay. Now what this is going to be less than or equal to the distance between actually I can just write it out fully a little bit more, not skip a step. Less than or equal to the maximum over, now if I just swap CP out for any point in C, minimize Q and Q, distance of CQ, and this is equal to the distance between C and Q, or C and Q. I said C and I wrote P. Okay, so this is now less, so that means distance between P and Q is less than or equal to the distance from P to Q. Wait, that's not what I'm saying. There we go. C plus distance from C to Q. All right, so that one works. Does anyone else have a guess? Maybe I'll give you a hint here. Here's the counter example. This is P. And this is Q. Which property of a metric space does this violate?
Just to be clear,
Mm-hmm.
in this Q is just some particular subset of P, right?
I just put it as it's a set. Sorry, this should be C maybe, just to be consistent with the initial thing we said. It's like a wiggly form of some small piece of P. Yeah.
Thanks.
Yeah. All right. So Dalton suggested symmetry, and that is true. Yeah. So for example, this point here, we'll realize, I probably shouldn't do that in the same color as the point set. Okay. There we go. Realizes the distance between, distance from P to C, and then something little realizes distance from C to P. So it's not symmetric, but we can symmetrize it though. Let's see. Note. We can symmetrize. And say that D, maybe let's put a star, Hausdorff of PQ is equal to the max of dPQ and dQP. Okay. And that is a distance. It doesn't take kind of the structure of P and Q into account. It just thinks of them as like point sets. But it's used a lot in I guess in geometry and in shape analysis to compare distances between shapes or as a baseline or data sets. Okay, so that was kind of, yeah. I'll put this in a green box. It's kind of gone off of my page, but that's okay. Okay. Okay, but what we want to do is we're going to go back to thinking about our algorithm here. We're given our point set. We want to find this set that minimizes this, I guess, the directed Hausdorff distance. And the greedy solution We mentioned what it was the other day, so who can remind us what our greedy solution to this is?
We pick a point in P and stick a point from C under it, and then we find the point that's farthest away from any point. Find the point in P which is farthest away from any point in C, and stick another point under that one, and keep doing that until we reach K.
Right. Yeah. Exactly. So we just start with any old point, with a point in P. Yeah, we're given P. Find. Actually, let's just put this here. Okay, so find K centers of, and it's going to take as input P and the value K. And C is going to be an array initialized to, say, P1. Of course, this is going to be of size K. Actually, I want to make sure that this is clear when we look back at it. So let's try to keep things in one line. An array of size K, and we'll say that C1 is equal to P1. Okay, and then I'll put a little comment here. Now we find C2 through CK. Okay. And we'll say while put this here. I is equal to 2. While I is less than or equal to K, what are we going to do? Well, for J equal, for each of these, J in 1, 2 to N. The P is an array of size N. Let's say that compute distance from PJ to C, and it's actually going to be C1 through I. Oops. Let P star I'll just say here actually C I is going to be the P and P with maximum distance. We're going to increase I, and while return C. All right. So, okay, does that the claim here is this returns a 2 approximation of the optimal result. And for a proof of this, I'm going to see Piazza. Yeah, so I think, yeah, for the next homework, one of the things that you can do is it's going to be responding to questions on Piazza about questions in chapter 3, but this could also be one of them, and I'll make sure that's clear there. But I'll help you walk through the proof of showing that this is a 2 approximation. But the main thing here is that, like, yeah, this is an algorithm, we can do it, right? Say no loop invariant gets us to the post condition that we've minimized the distance between the point set and C. Okay, so we analyze it from that respect because it's not answering the question we want. It's approximating the answer to the question we want. Okay, and why is that? Because this is an NP complete problem or NP hard problem. And this is one place where we do see greedy algorithms come up a lot, is where they're like, you know, the greedy choice is not the best one, but it gets us pretty close, which is nice when that happens. Okay, do you have any questions about this algorithm? Going once, going twice. Okay.
There's a question in the chat.
Oh, there is. Oh. Yeah. What is a 2 approximation? Sorry, I had it open because I figured, oh, I'll see it because sometimes I don't see it, but it doesn't give me the like red blurb if it's open because it assumes I'm just looking at the chat, I guess. What is a 2 approximation? Okay, good question. Let's write this definition down. Of 2 approximation. Okay, so and I'll write it in terms of this. Suppose C, I'm going to put G here, is some solution to our problem. Okay. Say the greedy solution, right? Okay. And then suppose CO, we'll put opt, is an optimal solution. Okay. And these solutions are trying to minimize something of some value. Okay, and we'll call it V of C is defined to be the distance let's call it V of C. We'll put the star because we could have a G or optimal. Right, in our case, V of C star is going to equal the distance from H to C star. Okay. And so we know by definition of C opt that V of C opt is less than or equal to the value of CG, right? Because C opt is going to be minimizing over every possible solution. CG is a solution, right? But we want to have, what about the other side, right? If V of CG is less than or equal to 2 V of C opt, we say CG is a 2 approximation of C opt. Okay, so it's bounding things on the other sides. And moreover, I can swap out this 2 with a different number, right? I can call it a 3 approximation if 3 is the number that goes in there too. So it's the solution within a factor of 2. Okay. Now, if the bound was on the other side, right? So if I knew, if the obvious thing, if I was maximizing instead of minimizing or something, it could be, we could flip things around a little bit, but it's the main thing that they're within a factor of 2 of each other. Cool. Good questions. Thank you for stopping. All right. So yeah, so in the in Piazza, what I'll do is I'll kind of post an initial question that kind of gets us started towards proving that this is a 2 approximation. And so things like this you would see often if you were in a like complexity or maybe in a theory class too. But at the grad level, you might look at more approximation algorithms and such. Cool. So I think what I'm going to do is I'm just going to start another board. I'll move it over here. Name. Okay. All right, so We'll just resize the boards to fit what I did today. There we go. Beautiful. So yeah, so this book is not, the problem we just discussed is not in the textbook. But I thought it was important to kind of look at one of the cases where greedy outcomes really come up all the time. But yeah, and also there's, you can read the textbook. If I could be just exactly what's in the textbook, what's the point? It's often nice to hear it verbally in addition to being able to read it, but I like to also try to give different types of examples, so that way you can hear things from my perspective as well as from the book's perspective, so then you get a more complete view of things. One of the big differences is Jeff Erickson's book doesn't focus too much on the correctness, and he even explicitly says that you don't always need to give proof of correctness for him in his classes. But in my classes, I tend to focus more on that and thinking about the loop invariant, because to me, it's helped me think through a lot of algorithms and make sure I don't do things correctly. It's the way I was trained in learning how to analyze algorithms. But yeah, so this next example is one from the book, and let's see, what section was it? 4.2, yeah. And we'll call it class scheduling. He gives some introduction that talks about trying to get all your classes finished, and this hypothetical degree you're getting. I'm going to start with the mathematical formulation, and then we'll think about places where this type of problem comes up. So, given, two arrays, you know what? A set of tasks and we'll say with n tasks. With start times and end times. Okay. The data structure we might want to use is two arrays, S and F1 to N, such that the ith task starts at Si and ends at F sub I. So I'm just going to use this S sub I as like a subscript here to kind of mean if we're looking at S at I. Okay. Less characters are a little bit easier for me to write as we're doing this. Okay, so this is what we're given. We're given a list of tasks, and we want find a maximal subset of the tasks such that no two tasks overlap. Okay. Return value is a subset of 1, 1, 2. Okay.
I have a question.
Yeah.
Is this maximal subset just referring to the size of that subset, like how many elements it has?
Yeah. And you know what? I don't want a maximal, I want a maximum. Yeah, good point. Note. Here refers to the number of elements in the return subset. And then we have maximal versus maximum. Right. I don't know if we've discussed this. It's a kind of like a subtle thing. Does someone want to explain what the difference between maximal versus maximum would be here?
This is a guess, but would maximal maximize the like total number of hours? Like considering the
They're
length of
both
each
referring
task?
to just to count the number of the sizes. Yeah, so it's not, yeah, we don't care about how many hours are filled up. Just how many tasks. Try another guess.
Would maximal refer to tasks that start later in the day? Like taking the higher end of the set?
I'm gonna put this here. Maximal subset versus maximum. Okay. So this is my time. And these are some tasks. And they all have start times, right? So here's S1, F1, right? S2, F2, S3, F3. So first, what is a maximum subset here?
Um, 1 and 3.
Mm-hmm.
And also 2 and 3.
Right. And here, the maximum subsets are also the maximal subsets. So we have 1 and 3, or 2 and 3. But if I added this fourth one, F4, S4, I could also have 4 as a maximal subset. And why is that? Longer duration is, again, we're not really taking the duration into account. So I could also have something like this. I'm going to do the same thing, S4, F4, and then S1, F1, S3, F3, S2, F2. Yeah, so in this case, the other one is a longer duration. What this simply means here is that no more tasks can be added. Right, and maximum is global. Right, so in other words, and for this case, we call it local. Biggest over all maximal subsets. Okay. Yeah, but then this does bring a point when we're scheduling things. We often care about like the time that something's running, or maybe also the time that something's not running. So the time, like we want to maximize the open time slots or something like that, while also still getting this. So there's other types of scheduling that you would account for the durations, but the thing here is we actually don't really care about much about how exactly when these times are. We just care about the order of the times, and whether or not two tasks overlap. Okay. Does that, okay, so what we want though is we want our algorithm to return one of these two maximum subsets, either 1, 3 or 2, 3, but not that maximal subset 4, right? So already we can kind of see like, oh, if we just try to add them at random, right, we could get into not returning the best one. So this kind of shows us if we try to add at random, we could make a wrong choice, right? Right. And as Nathan said there, if we add at random, I'll say here, AKA, choose one to start with. Choose next one. If overlaps, ignore. If not, add to subset. And add. We're going to make sure to, yeah. Repeat until reached end of the tasks. Okay, so this is the solution that's just not gonna work because I could choose that long or that one that overlaps every other one at first, in which case we can't add any more. And there's no undo version here. But this kind of leads us to one. Let's think. There is a dynamic programming solution. Let's think about that. Okay. So if in the dynamic programming, the way we think about things, we want to think about what is this recursive structure, right? So what is this? What is the potential recursive structure that that we could use to solve this problem?
Should we be thinking of a greedy recursive structure or not necessarily?
No, we want a recursive structure that gives us the answer. Yeah, so don't worry about greedy yet. So we've already thought like, okay, well, what if I just choose one at random and add it, right? Now we've seen this before when talking about dynamic programming, right? We try to add it and see if it works. And then we try not adding it and seeing if it works. Would this work in this case?
I think so, yeah.
Yeah, so let's write this down then. So if we have, if we say schedule, okay, our set of tasks. And so I'm just going to do this here. This is set of tasks. So T is equal to our array of start times and our array of finish times. Okay. And we can try to add it. Okay, so how do we try to add it? So we try to say, I'm gonna add a helper thing here. We'll call it R, maybe a return value here. We'll call these required tests. So if, we'll say none of our required tests overlap. Okay, so if T is empty, it's going to be R if T is empty. Okay, it's going to be schedule We can try to add it. So this is t minus, or I guess we can say here. We'll try the 2 through n, or, and then r union ti. Oh. I need to make this a maximum though. Ah. Oh. Okay. We try to add it and then we try not to add it. So T2 to N R. Try adding. Not adding. TI. Okay, and then our initial call. Oops. So we have it here. Initial call is schedule T is equal to schedule T empty set. So we require nothing. So now we have a recursive solution. And how many ways will we see schedule of TR called? Oh, here we go. Is this search exploration call considered greedy? This is not greedy. This is just a recursive formulation, and it's trying everything, right? So we would call this exhaustive if it's trying every option, really. It's not 2 to the T, right? So, question. There we go. How many unique ways to call schedule T, oops, of R, T comma R? Well, how many different options are there for T? Yep, N. So there's N options, right? Because we're going through. And how many options are there for R? Well, really, we could have any possible subset. So this 2 to the size of T was not 2 off, right? So it's 2 to the N. Right, so if I were to do this recursively, this would be exponential, right? So that means that we have n times 2 to the n ways to call. But we're not going to actually look through every one of those. So the DP has runtime. And I'm gonna put this as O to the end. Has runtime and cubed. Why? I'll put here, let's discuss on Piazza. Okay. So yeah, just in the interest of time, because I want to kind of think about this as the greedy solution too. But we can analyze this, we can continue this thought here down this path of thinking about it as a dynamic program and try to figure out what the optimal, what the runtime of that would be. So, but now we need a greedy solution that will work. And so we have about 7 minutes left. There's various solutions that will work and won't work. So I think one way we could do it, and if you guys guess it on the first time, I'd be super impressed if you haven't seen this before. So if you've seen this algorithm before, maybe let someone else answer first. If you're right, I'll let you know. If you're not right, I'll hopefully be able to quickly find a counter example to what your algorithm says. So greedy algorithm. Right, and so we're going to pick one each time, right? Pick anyone. Each time we'll iteratively add. I'll just say it as iteratively add and never look back. Okay, so we never backtrack. We never say, oh, we made a wrong decision before. Let's remove this one and continue on, right? So we're always just, and so if we already saw that if we pick anyone at random, this doesn't work. Right, and the example here was, right, and so here's a big one. I'm not going to put my SIs and FIs on it because we've seen this before. So this is one that didn't work. And you can also like suggest different ones that you know don't work. And if you don't have a counter example, let's see if we can come up with a counter example too. So you can say, what if we do this? So go for it. Let's hear a couple more examples.
Could you do it so that like you decide to include something based off of the number of tasks that it overlaps with?
Okay, so you're saying that pick the one that has the least number of overlaps with other tasks. Is that right?
Yeah.
Okay. All right, well, I can do this again, a quick poll. Oh, wait. Pick least number of conflicts. Works. Doesn't. Not sure. Uh-huh. There we go. Okay, while I think of whether or not this works. Leaves number of conflicts. We have a whole lot of not sures on this one. um, so I'll show you the result here. It does not work. So let's see if I can come up with a. There we go. I did it. Okay. It's a little nerve-wracking to try to come up with counterexamples on the fly. There you go. So if these are such that I'll put on, these are the number of conflicts, right? For each of them, I'm going to label it by them. And so this one, it conflict with 1, 2, I guess 1, 2, 3, 4, 4. This conflicts with 1, 2, 3, 3, 3, 3. And this would be the same, 4, 3, 3, 3. Okay, so there, if I pick it, it's going to be this longest one. Good example, though. Yeah. So and for this one, it's kind of like there's all these really bad ones that don't work. But here's the real one: is to pick the task with the first finish time. Yeah, so that was the, okay, so I'm following up with Nathan there. So he was saying iteratively add non-overlapping fewest conflict tests. That was this suggestion here, which we already saw. If we first add the long one, because that has only 2, we kind of wound up in a local maximal solution and not the global maximum. But if we iteratively, if we kind of sort by finish time and choose the first finish time, then we will then the earliest finish time that doesn't overlap with that, and so forth. And you can already see that we're inclined to think about this in a stays ahead type of way. All right, so I'm going to post two questions that I promised you on Piazza, so that way if you like these problems and want to kind of think about them more, that you can work on those for your homework. So the homework is kind of open-ended. It depends on which problems you find most interesting. So hopefully this will work well for you. And I'll see you next week. Bye.
Thank you.
Thank you.